idea behind this code is that you need to use the feedback command in a very specific way, because you will be feeding back now 2 signals as opposed to only 1, as you've done up to this point. So I just fixed this here for you. I just wrote this for you so that you don't have to go into the documentation for the feedback command and start looking this up. I just did this for you, and I'll try to explain how you're using this. All right, because we're gonna do velocity feedback. So let me go to my simulation so that we can start telling the story, so that I can start telling the story about what you're supposed to see and why we need this velocity feedback concept. So let me get into this. Here's the MATLAB. All right, so this is the same thing, the motor characteristics. These are the same things I used for the previous assignments. Below here, I have the transfer functions, the position and the velocity transfer function. So this is the first time we're going to actually use the velocity transfer function. Before, we only use the position. So remember what the general idea of this is, right? You cannot get lost into the abstractions and start to be, confusing yourself. What we are after is, understanding a very, very simple system, which is just this motor here. Where's the picture of the motor? So you have a motor. This motor outputs a voltage given, from a transducer, which measures the position of the motor. And this transducer or sensor gives you a voltage proportional to the position of the motor, the angular position, because this is a motor, so it's spinning. So we are measuring the angular position. Where's this picture here? Right here. Do not be confused by the abstractions. This is a very simple system. Your motor is right here. Over here, we have a mechanical reduction. This is just to slow down the signal so that we can actually use this position measurement or this sensor. So this thing here on the right, this is measuring the angular position of this motor, because sometimes you just want to turn the motor so that it stops at a specific angular position. Imagine this is the motor driving an antenna, for example. One of these antennas that, or tell us, things that look up into the clouds, right? Some kind of sensors or dishes that move around. So suppose this is the motor that drives this antenna. So you may want to start turn the motor just a specific amount of angular deviation so that you stop at a specific angular position. So this is how you can think of this. This is just a motor driving. It can actually drive any kind of equipment that you want. So we can measure its angular position using this sensor. So this sensor will give you a voltage proportional to the position. So this is what you are seeing here. Whatever you get out of this is just a voltage whose magnitude is proportional to the position of the motor. This is the output, Y, and the input is just the ideal position that you want to reach. So if you have a step input, which just goes from 0 to 1, we can always scale this unity step response so that we can get any arbitrary position that we want. So this input here, the step or the square wave, corresponds to a specific angular position that you want to reach, or the desired position. So we close this loop so that the output is as close as possible to the desired position, which is the input. So if you look at something like this, as you saw before, let me run my code here, because we're now gonna study a new player into these responses here. So this is something we've seen before. So what I'm talking about is this blue input. This is the step. This blue signal is the step input, which is the desired angular position that we want to reach. The step response is this red signal here, which is in our schematic here. This is the output. So this is the output. This is the desired input. In the figure here, they are shown in red and blue respectively. Where's my figure here? So the output is red, the blue is the input. So you see the motor starts from rest or from 0 angular position, and when you input this step, the motor starts moving. You can see my arrow here, my cursor, so it starts moving. And then because this is a physical system, depending on how you drive it, you may have some overshoot here. So here you can easily see the system just overshoots. But eventually, if you allow enough time, the output coincides identically with the input, which means the position that we wanted to reach has been reached by the system. So this is how you should be interpreting this, right? The motor spins from zero angular position to reach the unity angular position that we want to reach. And eventually it has some overshoot here. Then the overshoot becomes the undershoot. You have some undershoot here. And then eventually you settle down into the position that you want to reach. So this is the goal of this system, right? We want to move the motor from a specific angular position to another destination. And we want to see how fast we can do this and what kind of response we get for particular controllers. In this case, all we have used is this, the proportional controller. So what you saw last time, let me start changing my values here. This is Kp equals 20. I'm just reviewing what you saw last time, and this is something you're supposed to see here too, so that you can give us the whole story. So let me make this Kp equals 5 or 2, for example. So all I have in my loop is Kp equals 2, and I get this response. Look at how slow it is. Remember the desired position that we want is the blue one, and this is the actual position of the motor. You see how it slowly creeps up to the value, and in this time axis here, it never reaches the position, although if you allow enough time, it will eventually reach the maximum position. Now, this is because the Kp is equal to 2. How about if we make it 5? We saw this last time. I'm just going to quickly go through this so that you can see, so that I can introduce the following concept, the velocity feedback. Notice for Kp equals to 5, notice how this is slightly faster. There's no overshoot here anywhere, but it takes a little bit of time for this output to reach the desired position. So if Kp is equal to 10, we're just making this bigger. Notice how we get a little overshoot here, but very little undershoot. There's almost no overshoot here, but eventually we settle down into the desired position. Now let's make this 15. Well, let's make this 20 right away. So you see, as you keep increasing the gain, you get faster responses in the sense that the alignment time becomes smaller or shorter. Remember, the alignment time is the first time these two signals cross, because this is the first time that they are equal, right? When they first cross, this is the alignment time. Why alignment? Because the motor is spinning, we want to reach a desired position. So the moment the motor reaches this particular position, that means it has aligned with the position that we wanted to reach. Although because of the inertia, this thing actually overshoots, as we see here. So that's the story for assignment number 2. This is what you should have seen. And I asked you before to go from steps to square wave inputs and to triangle wave inputs, if that was the case for that particular assignment. So now, before we actually introduce velocity feedback, can anybody here interpret how this would actually look like if you were looking at the motor as opposed to this particular response that you see here? So suppose I just fix the gain and I start the system. Where would I see this change? How would I notice this in the actual motor? If I were just looking in the lab, if I were looking directly into this motor is spinning, this is just outputting. So you can think of the voltage that is being output from this sensor as being the signal that we have here in red. So this is the output, like I said. So this is the voltage proportional to the position of the motor, which is the same to say as the output of the sensor, whatever sensor is measuring the position. So how do we interpret this kind of change here, where you see this thing increasing and then it stops here and then it goes the other way, namely it decreases? How would you see this physically in the motor? How would this act up if you were looking at this? Anybody? So remember, the motor is just starting from a given specific position, right? So this thing starts spinning. Let's assume this thing starts spinning clockwise. Let's just say this motor starts spinning clockwise, like this, clockwise. So this is what we are seeing here. The motor is slowly turning clockwise until it reaches a specific angular position, but at some point it does this. How do we interpret this change here?
Would that be?
Yes, very good. So this is how you would physically see this output, right? Because remember, this is the position that you are seeing, right? So initially you go from 0 to a specific value here where you see you have this peak, right? But you see eventually after this peak, it starts decreasing. So that means the angular position is decreasing, which if you are looking at the motor itself, you will see this thing reverse itself. So once you reach this peak, when it starts decreasing, you will actually see the motor spinning counterclockwise. So this is what I mean by you guys not losing yourselves in the abstractions that we are looking, when you're looking at the MATLAB, you should actually be able to correlate whatever you are seeing into a physical, phenomenon when you're looking at the motor itself. So this is how you should see this to help to make your life easier, right? This blue signal is just the voltage from the power amplifier, which is a fixed voltage, right? It just gets input into the system. Now, because this is a physical system that has inertia, you will see this kind of response for this particular gain here. So you can see eventually it turns the other way slowly, right? So at this point, it goes from turning counterclockwise to again spinning clockwise, and then eventually dies down. And when it reaches the position, you will see this motor completely still. So it will not be turning anymore because we are just trying to reach a specific position. And when we do reach it, we want to stay there. So that is why we study step responses, right? Because sometimes you just want to change the system from one state to another. And a step response is one way for you to figure out how fast or what kind of performance you will get if you put in a step command. That is the reason why we study steps, because of reasons like this. You want to move your system from a specific position to another. You want to see how fast you can do this and what kind of performance you get. You usually want to apply a step response so that you can figure this out. So all of these signals that we see here are not just simple abstractions. These are actually signals that we can interpret the model or explain the behavior or the phenomenon of the actual physical system. So that's good. Now, one signal that we have not seen up to this point is this green one. So now this is what we call the error of the system. So this is just simply the difference between the input and the output. Notice if we go to our diagram here, it's this guy. That's the error because this is the input or the desired command, and this is the output. So when you feed back the output, all of these two signals go into this junction where they get subtracted. So the error is right here. So this is what we are seeing now. This is the new player that we're going to start studying in our responses, the error, because sometimes it's easier to just look at the error to see what happens. So now let us transfer this explanation that we have for this and try to explain it as opposed to looking at these two things. Let us try to explain this using the error signal. And you'll see that this is another way to view it. But you have to understand where this error signal comes from and what it is telling you. So again, it's a very simple definition. The error is equal to the input minus the output. So if we understand this definition here, that the error is the input minus the output, let me go back to my MATLAB. A question for all of you. What do I expect the error to be at this particular point in time over here? Without looking at the green signal, at this particular alignment time, at this particular instant of time, what do I expect the error to be?
Should be 0.
0, because this is exactly what this is. And if you look at the error signal, if you drop a line from here down to here, you will see that this is exactly where the error becomes 0. And then because we have another instances of time where they cross, for example, here, you can see that the error is 0 also at this particular instant. And then we have several other instances of time where the error signal actually crosses 0 or the 0 horizontal line. And you see that eventually if you allow enough time, the error signal is identically 0. So you guys can see that by looking at the error signal itself, you can actually see how your system is performing, right? In a different, or interpret this in a much more concise way by just studying the error. So we know that by looking at the error, that because this error is really big here, this particular instance of time, we can see that this is actually where the maximum value is. I mean, given that we start at this particular initial condition, because we can move this initial condition here and see what happens when you start turning the motor, right? It will probably not follow this horizontal line. But because of the initial condition, you can see that the maximum value of the error is actually right here, right? Because this is where they are most further apart. The motor is starting at 0 angular position, and this is at 1, whatever this 1 means, right? Remember, we can always scale this thing, so 1 does not mean exactly 1 degree or 10 degrees. It can be anything, right? As long as we scale it. But we can also change the initial condition and make this, smaller. Well, you see, where eventually, as the system has time to evolve, eventually the error converges down to 0. So notice all these terms that I am using: the error converging to 0, the alignment time, the overshoot, right? All of these terms may sound familiar from EE 371. And now the beauty of this class is that you are actually, interpreting these terms in light of a very physical and particular system here. So this is what we're trying to do in this class. All right. So we are here. Now we know what this is. Now we can interpret this overshoot here in terms of how the system can behave. So now, this is a good place to introduce the velocity feedback, because some of you may wonder, okay, I understand this. I understand that for very slow gains, we have a very slow system. I mean, for very small gains, we have a small system. As we increase the gain, we get better responses. That means, better in terms of faster responses, right? But we also saw that higher gains lead to instabilities, may lead to instabilities. So you have to be careful with the gain. Now you may ask yourself, okay, can I fix the value of my particular KP? Can I fix one value? And can I do something else so that I can reduce this overshoot without changing the value of the KP or the proportional controller? And this is where velocity feedback comes in. So what we are going to do here, remember, this is the system you have been studying. So what we're going to do is, in addition to feeding back the position, we're now going to introduce a second channel where we feed back the velocity of the actual motor. Remember, you may be confused as to what velocity and speed means for this particular system, but because this is a simple single input, single output system, you can use these words interchangeably. You can say speed or velocity, it doesn't matter. When you have a multiple input, multiple output system, then you need to be clear onto what you mean, whether it is speed or velocity. But in this case, these two terms can be used interchangeably, and you should do that. So this brings us to the schematic that I have here for you in assignment number 3. So let me walk you through this. This is the motor arrangement. This is the 360-degree potentiometer. This is supposed to be the schematic for this guy. Oh, I lost it. Oh, no, it's right here. So this is this guy. This is your 360-degree potentiometer. So this potentiometer gives you a voltage proportional to the position. Now, we have the tacho generator. So this thing will give you a voltage proportional to the speed of the motor. So this tacho generator is actually over here. This little guy is this wire that is coming out of this is going into the tacho generator. But we don't need to know where it is. We just need to know that this is connected to this motor, and we can measure its speed or velocity at any time. So this is what we're going to do. We're going to introduce this second feedback channel, and we're going to see how this helps us, if at all, in reducing the overshoot while keeping the fixed gain from the proportional controller at a specific value. So this is the idea, or this is the story behind velocity feedback. We're going to see how this helps us, if at all, in reducing overshoots or anything else. And this is the following error, and we just, we just introduced this term. We're looking at we know what the error is, right? But we don't yet know what the following error is, or what we mean by this. This will come in assignment in tasks 2 and 3. So let us just go here into my code and try to study the effects of velocity feedback. Notice how I'm telling you a story. Each time we introduce a new concept, we have to relate it to something, right? Or we have to know exactly why we would introduce such a thing. I'm not just telling you, oh, this is velocity feedback and this is, you should use it, and then it will give you a specific performance. We want to be able to relate it to something so that we know why we need it in the first place. So let me just set up my code here. All right, so this is the image or the response we're gonna start out with. So now let me walk you through the code. In the assignment that I gave you, assignment number 3, you have this code so that you can just copy it into your MATLAB script and you can run this and you should be able to reproduce this exact figure here. Now let me correlate or let me link up this M script with this schematic that I have in the background here. So what I have here is my usual KP gain, which we now understand. If we talk about a proportional controller, fixed proportional controller, we should know by now, all of you should know by now what this thing can do for you. And you also should know that, you have to be careful when you use it. So this KP will be this channel right here. Eventually it will go here. So that will help us control the KP gain. So now this knob here, this is an attenuator. So this gain, we will now call KV. So this KV is in our code given by this line here, line 28 in my particular code. It might not be the same line in the code that I gave you in the assignment, but you will eventually be able to use it. So now notice how KV is equal to 0 for this particular figure that you are seeing now. For this one, KV is equal to 0. So that means this attenuator has been turned all the way left or counterclockwise so that it gives us, so that there is no signal going through here. So when KV is equal to 0 in your code, you should be thinking of this physically and saying, okay, KV equals 0, that means there is no velocity feedback going back to the summing junction. Don't worry about what this is. This is just the way you actually physically set this up so that you can have the signals come in and be added or subtracted accordingly. In other words, this will give you whatever this does, which is a summing junction. We call this summing junction even though you have a minus here, right? I mean, because these things are just work on the same principle. So this is a summing junction. Two signals come in here. So now because we have an additional signal that we want to feed back, we need to extend the summing junction. And this is the way you would see it in the lab, using this op-amp and several input resistors. But pay no attention to this for now. KV will be right here. So you should be making a note as to what KV is doing for us here, right? So now you see that if KV is equal to 0, we have nothing but the system we already are familiar with, the KP proportional gain. So if we make KV non-zero, this essentially means that we will start letting this channel become active, and then some velocity feedback signal will actually go back into the summing junction, and it should show us something. Or it should do, let us see what this does. Without me telling you, I'm just going to go into the code, but you guys have to understand what I'm doing here. This is the signal, this is the figure we're going to start with. KP is equal to 15. As you see here, I have a lot of values here that I want to test out, but eventually I will do that. So KP is equal to 15. KV is equal to 0. So that means this is a system we already know, and this is nothing new. But now if I comment out this KV value of equal to 2, try to see, guys, whether you can, let me just run this again so that the image doesn't change very much. All right, so this is what you will get for KV equals 0. Now this is KV equals 2. Pay attention to how this figure is going to change. Let us try to see whether you can see what's going to happen with this thing. I will refrain from making comments until I try all these values. Hopefully you are seeing what something interesting happened here, and you can make a note of that. So now KV is equal to 4. So I'm just incrementing this KV in steps of 2. Let me make it KV equals 6. KV equals 8. And finally, KV equals 10. It's pretty obvious what is happening, right? This is KV equals 10. So now let me comment these things out again and go back to KV equals 0, which means no velocity feedback. All right. Can anybody help me here? What did you see happen here when you increase the value of the KV?
The overshoot decreases.
Yeah, I mean, you see a significant decrease in the overshoot, right? So that means you're actually providing more information so that the motor slows down before actually overshoots. So the idea behind velocity feedback is that you can actually keep particular fixed gains here, and so that you can don't reduce the alignment time, but at the same time you can make it provide this velocity feedback information so that you can do something about the overshoots that you have here. So this is the effect of velocity feedback. Now, how should you be interpreting this physically? Well, this is the velocity of the system. It is being fed back, and we are somehow using this to help us get better responses without changing the proportional gain. So this velocity feedback acts as a predictive signal that tells the motor to slow down before the overshoot. So what happens is, at this particular case, when KV equals to 0, that means no velocity feedback, and KP is equal to 15. You guys can see that when at this first alignment time, right, the motor reaches this position, but it overshoots it. That just means that the motor has, the velocity of the motor at this particular point is just too high. So that is why, because of the inertia, it cannot just stop instantaneously. So when you introduce the velocity feedback, there's a nice theoretical background explanation behind this, and this relates to what I'm saying now. So you may want to read that in the appropriate chapter that you have here in the manual. So this velocity feedback signal acts as some predictive information that tells the motor to stop or to reduce its speed, so that it can actually don't have as much overshoot as if you were not using the velocity feedback. So there is a nice intuitive way to understand why you want to use velocity feedback. You can even, see this when you are driving your car. Suppose you want to go from position A to position B in a straight line in the fastest way possible. So what you do is you want to eventually, step on the gas, and then when you're closer to the destination, you want to slow down so that you don't overshoot the mark. Because you guys know that if you're driving at 60 miles per hour, when you press down on the brakes, you will not stop right away, because the car has inertia and a lot of things are happening, right? So if you're going to at 60 miles per hour and you want to stop suddenly, you better slow down, before you get there. You cannot slow down right away from 60 miles per hour. So this is what, your eyes and the road, you're actually feeding back the velocity of your car. So this is a similar concept here. Velocity feedback is very helpful for this, so that you can predict what's going to happen and and use this information to your advantage, so that you can reach the position in a much with better performance. And you may say, oh, okay, this is very good, but you will see for the other assignments that this is not really perfect, because you're only dealing with the step response. You can actually see that when you change the input to a square wave or to a triangle wave, velocity feedback may not be as useful as you may think. But this is the real goal, or the real usefulness of velocity feedback: reducing the overshoots, which means just using the information that we have about the speed of the motor so that we can actually control the motor in a more with higher performance, or better performance rather. So this is what you will be seeing here. This is the story. You will play around with the KV gain, and you will try to see what happens as you do that. You will also be asked to do square wave responses. Now, note that this is only the step response, but you see that the square wave response is just a combination of these steps, right? So you can do that in the assignment here. That is the story for task 1. You are given this code, which you can easily use, and then you will be able to reproduce this response and then change the KV gain to see how this actually helps you mitigate the effects of high gains. So velocity feedback can be used in conjunction with high gains for the proportional controller, so that you don't get as much overshoot, but at the same time you get the fastest alignment time possible. All right, so that is the story behind task 1. you can just read these items here so that you get more details as to what kind of responses you would be expecting. In this case, it'll be idea to do foliations for your images. Otherwise, you'll get just too many pictures, right? So if you want to do a foliation for this, this is the perfect time to do that, or the perfect assignment to do that. I explained what foliations were last time, right? I think I did. All right, task 2. So what will happen here now? We will actually change the input from a step. I actually should have shown you the responses for a square wave. I think I will do that. Let me just set up my code here so that you can see the responses for this same system as opposed to steps. We're going to introduce square waves. So let us see what this is going to give us. All right, so this is the square wave response. You may notice something here. Notice how the overshoot is smaller here than in the other particular instances of time where the input changes too. This is due to the initial condition, right? I mean, this starts over here at 0, and it only has to go from 0 to 1. So that is why you don't get that much overshoot. But look at this particular case, this red line. The position of the motor has to travel from 1 all the way to -1. So that is a 2-unit difference as opposed to a single unit difference. So the farther away from the final destination you are, you may need an additional push for this. And if your gain is too high, you will see these high overshoots here. So this is the response for this for Kp equals 15 and Kv equal to 0. I will not do all of these cases, but I will go from Kv to Kv equals 6. Maybe let's do 4. So now this is Kp 15, Kv 4. Look at this beautiful thing. You see how this thing adjusts itself? You can actually see the apple getting closer and closer to the input, to the desired position, right? All of this without changing the Kp gain and only introducing more and more velocity feedback. So this is pretty cool. Even though we have Kv equals 4, we still have some overshoots here, right? We have some undershoot here. Now Kv equals 10. I will not do all these values. This is for you to do and convince yourself how of the usefulness of this system. Now this looks pretty interesting, right? Look at this. So your task will be to interpret this in the light of the physical system that you are controlling, right? Even though these may look like capacitors and the behavior of a capacitor that you learned in your previous courses, you should not be talking about capacitors, right? Because you're actually studying this motor. So you should be able to relate what this figure is telling you to the behavior of the motor itself. And now remember that we have a third player here. We have the error signal. So if you don't want to look at the difference between these two, just try to focus on the green signal and try to explain it from that perspective. So that is also part of task 1. So now let me move on to task 2. Let me just set this up. For task 2, I need Kv, a particular Kv equal to 0 so that I can prove a point. And then I need this to start from 10. And for this, I want to get rid of the square wave because we don't need it anymore. And we're going to use triangles for tasks 2 and 3. All right, let me just run this. Oh, I think I need to scale this here. Okay. I have this set up here. I just want to make sure that I have all this so that we can have a nice picture here for this. This has to be Kv equals 0. All right, so this is the response for Kp equals 1. What do we see here? Do not be confused as to what you are seeing here. You see that the gain is too small for this, right? Look at the response for the input. Kp is equal to 1, right? And this is the actual response, and the input is the triangle, the blue triangle. This is the desired input. right? So now let us make Kp equals 5. You see, as you increase the gain, you could argue that the red signal is starting to look more like a triangle waveform, right? I mean, it doesn't look like a triangle, but it's getting closer to it. Let me see here. Kp equals 0. Yeah, this is correct. So now you're supposed to try all these gains here to show you, to get you used to what you see when you change the input from a square wave to a triangle wave. You see the performance of this. You see, this is more clear when you introduce higher gains. Look at this. It's getting better and better, right? This is the blue one is the input, and you guys can see that this signal here is starting to get closer and closer to the input, which is in a sense the same story that you saw for the for the square wave, right? Well, now the main difference is that this kind of input is more demanding. Why is it? Because the square wave, for example, or the step, it just has to reach a specific value and stay there. When you talk about the step response, it goes from 0 to 1, and then you're supposed to stay there. Now this input, which is a triangle waveform, is more demanding because it is steadily changing. So this means that this position is steadily increasing, and then it reaches a maximum value and then decreases the other way. So this is a more demanding input. And notice how the controller responds. This is the Kp controller. Notice we have a lot of error here, and the error is smaller over here because you can see that this is 0 here. This is where the error touches 0. So this is just the story about what you're supposed to just see how this system responds to a triangle waveform input. Let us see Kp equals 30. Closer and closer, right? As I increase, when I say closer and closer, you should be convincing yourself that at this particular instance of time, for example, here, 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 and here, this is where the output and the input are closest. And somewhere at the peaks, this is where they differ the most, right? All right, let us do Kp equals 50. So this is the story for task 2. You have a more demanding input, which is a triangle waveform, which steadily changes. You're supposed to just change the Kp gain and see how you what kind of behavior you get. So this is very similar to what you saw for the square wave response. If you keep increasing Kp, you will get better performance, but if you increase it too much, you will get something like this. Do not call these oscillations in your report because these are not oscillations, right? This is just the performance of this. This is just too wobbly. It goes up and down, right? It crosses the input, but it's just too fast, and then it tries to recover. But this is what you see for Kp equals to 50. So now the task for assignment number 3 is what happens when we introduce velocity feedback to this kind of input. So for this, I think I ask you to keep Kp fixed to a specific value. Kp equals to 20. At this particular case, you see the best responses out of this so that you can interpret this. So task 2, you will introduce a triangle waveform input. You will play with the Kp value, and you will convince yourself that this is very close to the behavior that you saw before. Although there's something that you did not see when you were doing the square wave responses, right? And this is something you should pay attention to when you see this. We can say that this triangle waveform, if you look at this, it kind of has 2 phases, right? Phases as a phase. So it changes from a negative slope here to a positive slope here, the input, and you see this is how the system behaves here. But now, because the input is just steadily increasing without sudden changes, you can see that the red line or the motor has enough time for it to come closer and closer to the motor, to the desired position. But now, before the motor can actually reach the desired position, you notice the change here again in the input. So it starts turning the other way, right? And you see the motor trying to catch up here. But because this is really a fast transition, the motor doesn't change up instantaneously, and it takes a little bit of time to change. So that means that around this area, you will see the highest errors here, as you can see by the green line, right? You see, this is the highest peak for the zero line, and this corresponds to this particular interval of time where that is related to the fast transition in the input. Now, as time goes by after the transition, you can see that the input here, the red line, the input here is the triangle waveform, and the output starts getting closer and closer and closer to the input. And at the same time, you can see this by seeing how the error starts to approach zero, right? Eventually, you have an alignment time over here. That is why you see this. You see the error decreases from the or increases from a negative direction to zero. So that means in magnitude, the error is actually decreasing. So you see, eventually it reaches down to zero. So now why am I bringing this up? Because you will see the effect of the velocity feedback here. And you will see something very interesting happening in the other phase where this thing is actually getting closer and closer. So this is what I'm bringing up. In the transients or in the fast transitions of the input, you'll see the most or the highest errors. Now, when the input is just steadily changing without fast transitions, this is where you see the motor or the position trying to get closer, ever closer to the desired position. And it's the error is the smallest here. Okay, so we have highest error in fast transitions, and we have the smallest error in the steadily changing input, where there are no fast transitions. Remember, this input is more demanding than the square wave or the step, because this is steadily changing. You can interpret this signal as a steadily changing position. It is increasing up to maximum value and it is decreasing. Okay, so this is how you should interpret this. And you can see that this is the case for this. So now, what happens if we introduce KV for this particular arrangement? So in the assignment, you're supposed to let KV equals 20. What else do we have to do for the assignment? And then you just have to introduce or increase KV and see what happens. All right. So here we go. This is what we start with KP equals 20 and KV equals 0. So now let us do KV. Okay, so now before I do that, this is where the following error term comes in. We know what the error is, right? And now, because the input here is particularly more demanding, and the output is trying to follow the input, this is what we call the following error, because the input signal is steadily changing. It doesn't stop at a particular value like the step or the square waves do. It just steadily changes, and the motor is trying to follow it or to track it. So in this case, we're going to use following error, and this is its definition. It is just the error that you see when your input is more demanding, like this triangle input, and you see the output trying to follow the input. So what we see here in this green line, this is the following error. And I just discussed that there are specific intervals of time where the following error is the highest for the fast transitions of the input, and it's the smallest in the slow transitions of the input, or where there are no fast transitions. So now let us see whether this is the same thing, or this is the case when KV is equal to a non-zero value. Please pay attention to the figures, see whether you can make out something, or whether you can see what is happening here. This is KV equals 2. You may not be able to appreciate it right away, but if you are, when you have this in front of you, you should be able to calculate these differences explicitly. Oops, where did it go? Let's do 6. Oh, this is not even changing, right? Look at this. There's a mistake here. Let's go back. So this is the first case. We go from KV equals 0 to KV equals 2. Let me make sure there are no more. Yeah. So this is KV equals 2. It's barely noticeable, but I don't want to say what you're supposed to see. I just want to let you figure what you see before I make any comments on this. So this is now KV equals to 4. The response here is a little subtle here. Hopefully you can catch it. That's KV equals 8. And finally, this is KV equals 10. Did somebody see what happened? Can anybody tell me what they saw for this particular case? If you compare this KV equals 10 to KV equals 0, that's probably the best way to see what happened here. All right, this is KV equals 10. Let me run the KV equals 0 again so that we can see this. So remember, this is KV equals 10, and this is KV equals 0. So you guys can see how this particular instance of time, right, the overshoot is really high. I mean, this overshoots right away, right? And this is really farther apart from this. But the steady state is very close. I mean, I call this the steady state because this is where the input changes the least. It is just simply steadily increasing, and there are no sudden changes here. But when you see that when you introduce velocity feedback, focus on this part here. Focus on these parts where we have the steadily changing input here. Focus on these parts. See what you see. Of course, you saw that the maximum value of this output decreased, right? This is KV equals 10 again. Of course, the easiest change to appreciate is that the maximum value for this thing isn't, you know, as close as for KV equals to 0. But we see something else. Notice how this error is bigger here. For KV equals 0, right? You have this output steadily approaching the input for these phases where the input just steadily increases. But notice here, when we introduce velocity feedback, notice how the error actually grows for these phases. When I say phase, I mean, you should understand that I'm using this word, right? Phase. So the phase in the steady state phase, or where the input is changing steadily, when we had KV equals 0, we had the least gain, the least error, or the smallest errors possible. Now you see that when you introduce KV, right, for this particular input, the error at the when the input is steadily changing, this is the highest now. Look at this thing. So what is the story then, or what is the point behind all of this? You guys saw how this KV was very effective for the transients, right? And now you're seeing that this thing actually affects very much the steady states. So this is why we study this thing, or why we try to change the input, so that you can see that velocity feedback is very helpful for a specific phase or transition in the inputs, but it isn't very it doesn't act you know, adequately for all the parts or phases of the system. In other words, this technique is very useful for a particular for enhancing the performance of a particular phase and your response, or you have to be careful how you use it, because you may actually slow down other parts of your responses, as you saw before. So note, this is the value of KP equals 0. Notice how this line is closer and gets closer and closer to the input here. If we were to allow enough time, you would actually see that the red line touches the blue line, if you allow enough time. But for this particular gain and for this particular time axis, this is what we see. And you see that by increasing KV equals to 10, this actually grows, which is something that you were not expecting, right? So in other words, you need to know, first of all, what velocity feedback can do for you, so that you know when to use it and when to look out for, you know, when in the particular case, when it may actually make your response worse. So there's a trade-off. That's the point. You need to know that velocity feedback helps in the transients or in the fast transitions, as you saw for the square wave. But when you have a more demanding input, it may actually mess up or deteriorate your steady states. So this is what you will be seeing for, this is the story behind velocity feedback. It is a very effective tool, but just like the KP gain, when you have too much of it, you will see this happen. When you, same story for the KV, when you have too much of it, you will just slow down your system too much, and then it will defeat the purpose of using it. So there's always a trade-off with these techniques, right? They are very effective for particular cases, but they are not universally valid. And that is something that you will see for the PID. This is why we are doing because the PID needs to be tuned to the particular application or system that you're trying to apply it to. All right, so this is where we're headed for the PID. This is one of the very important building blocks. So velocity feedback isn't necessarily one of the, the D in the PID, because the D in the PID stands for derivative. What this velocity feedback is very closely related to derivative signal feedback, which we'll study eventually. But this is one of the building blocks. Understanding velocity feedback helps you really understand why PID controller is so effective and why we use it everywhere. All right, so that is the story behind task number 3. You have a chance to play with these responses so that you understand what's behind this. Again, there's a nice discussion behind about the velocity feedback action in the assignment itself for the particular chapter that we are studying. So you may want to read that while, when you sit down to write your report, or before you actually sit down to write your report, so that you can get more details as to how this works. But this is assignment number 3. Are there any questions? I gave you the code. Remember, you're supposed to just focus on the concepts. You do not get bogged down with lines of code or what each line of code is doing. Whatever lines of code we're using, either I discussed them before or they are just some general commands that you may have used before. So that is what this is, assignment number 3. Are there any questions before I move on to the other part of the other things that I wanted to say for this? So remember, you need to submit your report. So you should have done that by now, by 9:30 a.m. Any questions about assignment number 3? What the velocity feedback is supposed to do for you?
I have a question.
Yes, go ahead.
Out of curiosity, because we still haven't done, like, there's a third variable that we'd be changing, but we haven't touched that yet. But I'm sure at some point, depending on the system that we're working with, would there be it would be advantageous to be able to dynamically change these values, right?
Oh yeah, and that is this is a nice research direction. Dynamic PID controllers, and you need these things, right? But yeah. Go ahead. You want to finish your question? You want to finish your?
No, I was just curious because that came up in my mind. Just.
Yep. That is a very good point to make, because sometimes you may think, oh, the system is behaving at a particular instance of time. It is behaving this way, but somehow, for example, an airplane, right? An airplane is a more interesting system. For example, an airplane, it flies to very different dynamic pressures, to different, the sky varies, right? The pressure, the temperature, all these things have an effect on the system, so it behaves differently. So your control may not be able to tackle all these possible operating conditions. So you may want it to change, to adapt itself so that it can self-adapt to the particular condition that it's trying to that you're trying to control. So yeah, when you do varying PID, you're getting into the theoretical aspects, and we call these time varying controllers. And these require more theory to actually study, because these things, when you introduce time into the equation, you will see that you really, really have to worry about stability here, because all these theoretical concepts that you learn for stability in E371, the root locus, the Nyquist plot, the what else do you learn over there? Nyquist plot, the Bode plot. All of these things that you learn, they only work for linear system, which is what this is. Now, when you introduce a PID controller that changes its gains dynamically according to the operation condition, you need to worry about time. And time is a really, really, difficult concept to capture. And you cannot apply these linear techniques. You have to go now into Lyapunov theory for stability, and it becomes more complicated. And this is what research is about. You want to study, you want to propose specific control schemes, some of which may vary with time, right? So it becomes more interesting, but it is definitely it's out there. All right. So this is what you call adaptive controllers, because if you think about what we have been doing, right? This thing is an adaptive system in itself. So I hope all of you understand what the question was. So our classmate was wondering, can these things change dynamically? Can you have this system change? For example, in the particular setup that we have, right? For the setup that we have, we either choose a KP equals 5, we fix the KP, and then we study specific values of KV. So we are never dynamically changing the value of the gains once we choose them. So for example, for this simulation that I have run here, for this figure, so that I can put his question into context. For this particular figure, right, the system develops in time. It just plays out. But for this particular behavior, right, the gains are fixed. KV is equal to 20 and KV is equal to 0. There are cases where you want to make these time varying. So instead of a fixed number, this may be a function of time. So this may be a function of time and this may be a function of time. Now, when you do this, as I was saying, you need to worry about the stability of this thing, because you guys may not know this, but when you introduce time into the equation, right, a lot of things can change and a lot of things become more prominent. So we really, really need to worry about the stability of these things. So that is why we started PID, this particular PID, right here. Well, that is why we spend so much time on a PID, because it is so easy to understand. And we understand the stability issues behind a PID, which are just linear systems. And when you make these things time varying, they may still be linear, but because this may be a function of time, then everything becomes more complicated. So yes, these can be functions of time, and this is what you call adaptive controllers. Because if you think about this, this is also an adaptive system, right? Why is it an adaptive system? Because it measures the output information and it somehow uses it to produce better performance or to make the system, act in a specific way. So this feedback system is an adaptive system in itself. But we have what we call adaptive controllers, where the controller changes with time to adapt to the high dynamic changes in whatever system you are controlling. And because this is a simple motor arrangement, PID will suffice for us. But now when you have this, when this is an airplane or a missile or a rocket or a drone or something like that, it becomes more complicated. I even, I have friends that work in drone companies, and all they do is use PID controllers for the controllers for the speed, for the motors. Or that's all they do, because everyone understands PID. It's very easy to design, but a drone isn't a helicopter, right? Or it isn't a real sophisticated airplane. When you have more sophisticated airplane or systems or plants, then you may want to consider dynamic or adaptive controllers. So this is it is possible, and it is an interesting research area. So yeah, thank you for your question. That's very, very interesting to see how what we are doing actually has, practical and theoretical considerations to study here. So yeah, any questions? Any other questions? You guys can look that up, adaptive controllers. You'll see that this can actually be tuned, on the fly, and you'll get into the real nitty-gritty of what feedback systems can do for you. Any other questions?
And that video you showed us on the first day of class,
yeah,
where the plate was balancing that ball, is that using dynamic?
No, that is just a simple PID controller.
Okay.
Well, you see how effective the PID controller is, right? If you're just looking at this video, you may say, oh, wow, what kind of, complicated mathematics may be behind this control system, but it is just a simple PID. That is why I showed it at the very end of class, because, I wanted to put in perspective what you can actually achieve with a simple PID controller. Of course, you see, if I play the video again, you see how this guy was just softly pushing the ball away, right? You can imagine that if you hit this, very hard, the ball would just fly off the plate, right? So this PID just works within a particular, envelope or a particular set of operation conditions. It cannot work for everything, right? So it is a nice application of the PID controller. And if you look into the references that they have in the video there, you may actually be able to understand what they are doing after we cover the PID controller in its entirety because we're missing other terms, right? We only have the derivative signal, I mean the velocity feedback, but we haven't really discussed the derivative, which is for the D and the PID, and we also need to discuss the I, which stands for integral control. So the D and the I, these are the concepts that we're going to eventually touch upon so that we can put them all together to form the PID, and so that we can actually understand this thing, you know, concretely in terms of a physical system, and also theoretically because you have the simulations. So yeah, this video looks fancy, but you guys eventually, when you go through this class, you can actually go into these references and you will be able to understand what they are doing, at least in the sense of controlling the machine. So yeah, that thing is using a simple PID controller. Thank you for your question. I mean, this is how you should be thinking about the class, right? You can actually apply this to something. This is not just something, you know, so that you can learn and forget about it, right? Feedback is a really, really cool thing that it's everywhere. So you guys may want to, you know, and we're only touching the tip of the iceberg. There's so much behind this. Any other questions?
Can you please show the response of the system to a square wave input? I have a question about overshoot.
Okay, can you tell me a specific item in assignment number 3 or number 2, or you
I
want
think
a square wave? All right,
showing
let
the
me
square
set this
wave.
up. Can I use the same code that I have here?
Yeah, I believe so. We saw it before.
All right, so today, right?
Yes.
All right. So let me give you a square wave, KV equals 0, KP equals 10. I think I had a 10 here.
Yeah, without using KV.
Okay, so no KV. I think I have to adjust. This is the triangle waveform. This is the square waveform. And I want to do something like this. Let me see. Let me just run this. Oh, I need to adjust this one. Yeah, this is good. Does this work?
Yeah. So from, you see where the time is 6 seconds, how it crosses that the red line meets the blue line, right? And then the time when it's around 12, the red line meets blue line again, right? Well, no, at like 7 or 8. So the time between 6 and 8, is that considered overshoot, or is it just like a lagging time because the motor needs time to reach that?
I mean, in this case, the position is -1, right? Whatever that is. It's just, you know, if we center the motor, remember, I lost the picture. This vertical line, let me just put this in perspective, all right? So this is the 0 line. Any positions, if this arrow is pointing anywhere to the right-hand side of this, that is a positive number or a positive angular position. And if this arrow is pointing anywhere on the left side of this 0 line, that is a negative value. So when you get to this particular response, the motor right here, it's spinning counterclockwise because it's going in the other direction, right? You see the slope, right? The slope of this is negative, so it's spinning the other way. And or it's spinning one way, let's just say, so that we can just make the point of this. And because it is spinning in the negative direction, that means it's just spinning this way. I mean, counterclockwise. When it reaches this position, it spins the other way. It just turns around. So this, in this case, this is undershoot, right? Because it is just overshooting the mark. I mean, this is just, you can just call this overshoot or undershoot because it just really depends on what direction you are actually spinning, right? So you can just consider this overshoot because it is, I mean, it is overshoot because it is spinning in the other direction, right? In the negative direction. Or you can, if you are unsure as to what calling this undershoot or overshoot, you can just call it a deviation, all right? Or a non-zero difference between the two, which is why we introduced the error signal. So if you're not sure as to how to explain this or to how to describe this in terms of overshoot or undershoot, you can just say a significant difference in the voltages here on the magnitudes of the signal, and these are reflected by the non-zero value in the error signal. So because this is spinning the other way, this would be considered overshoot, right? Because it is spinning the other, in the other direction, in the minus direction, right? So you can call that overshoot. Some of you may think, oh, it is undershoot, right? Because undershoot would be if this had a little dip. Maybe, let me just call this, no, you wanted to see the square wave. So yeah, it doesn't really matter what you say about this. What you can call it overshoot or undershoot. When I read the report, I should be clear as long as you specify the values of the time here, right? So this is what, 7, and this is 10. So as long as you specify where or what particular interval you're talking about here, I should be able to understand what you mean by this, right? So it doesn't matter what you call this. You can say overshoot or undershoot, but it may be easier for you to explain it in terms of the non-zero value of the error. We can see here, right, that this is non-zero, and this is also non-zero. This is where these things actually overshoot here. So it doesn't matter what you call it, right? In one sense, it would be undershoot. In another sense, it would be undershoot, but it is just a deviation from the desired position, right? That is one way to refer to this if you are unsure as to how to refer it for your report.
Is there a name for the graph when it's from 6 to 7? You see that gap between the red line and the blue line before that overshoot or undershoot? What do we call that?
What do you mean? What gap? What? I don't understand. What gap?
Yeah, like move your cursor from there to the left, from there to the blue line. Yeah, what is that called?
I mean, these are different intervals of time. There's no these signals come at different times, right? This, if you're comparing anything close or at this particular instance of time 6, you should be comparing it to this one. There's no time, there's no technical word for this. Oh, I understand what you mean now. You wanna explain how far this is away from this, right? Or
Right.
the difference between these. So there's no technical name for this.
Okay.
Because, you know, these signals come at different times, right? Do you see that? I mean, this comes, whatever this is 7 something, or, you know, greater than whatever this is, which is what, 6? Yeah, 6. So there's no, what we care about is the alignment time, for example, right? The time when they reach, because, you know, this match or this alignment time corresponds to the same instant of time. These two intervals, I mean, because what would you measure? The gap between here or the gap between here? I mean, it would be just a very arbitrary quantitative variable, right? So there's no, we usually don't study that. What we study is the value of the deviation from the desired position. And this is something these are the terms that you use in EE 371, settling time, which I warned all of you not to confuse with the alignment time, which is different. So you usually worry about the vertical direction, the deviation in the vertical direction, not in the horizontal directions. That is, if you are measuring the time constant of your system, right? You also worry about the magnitude of this. So there's no time there is no concept or no technical word for what, you know, that you need to include in the report to explain this gap, because it is these 2 points are happening at different times, right? This is 7.37 and this is 6 point something. So there's no way for us to easily correlate these values. So there's no name for this. All right, you don't have to include it in the report. What you worry about is this maximum deviation, right? Because these happen at the same time. For example, whatever this is, 9.3 and the corresponding 9.3 over here. So you should be looking at this in the vertical direction, the deviations in the vertical directions. All right. Any other questions? This is good. I mean, you know, the more questions you ask, the better we can actually see what we are doing, right? Of course, you guys see this green arrow here, right? This is going up even further. This is I just clipped the picture here so that we can actually see it closer, right? But so some of this may have bothered somebody, right? And it would bother me if I just didn't know what we are actually showing here. But if I take this out, let me just show you what I mean. If I run this again, MATLAB would automatically fix the value of the y-axis, and it will show me the entire thing. I just decided to clip it here so that we can get closer and closer to the behavior of the system. I just decrease the y-axis for the plot to make it go from minus 1.5 to 1.5. So I chopped off a little bit of the green waveform, but that doesn't matter, right? We know that that's the highest there. So I just did this for me to be able to explain it to you, right? But you should be able to show whatever signals you have in your report, you know, in this entirety, because we don't know what may be happening there, right? So this would be a better picture to include in your report. Of course, I'm missing this thing is something that you should not do, right? Because this doesn't look very good. So in order for me to do that, I would need to put -2 here and 2 here so that I get a nice flush plot for this particular figure. So that doesn't matter. All right, any other questions? Feedback is a beautiful thing, you know, when you get into it. I mean, I may be biased, right? But it's everywhere. All right. Are we all set for assignment number 3? So here comes what we're gonna do next week. We're gonna go into the lab next week. Are you all ready for this, for the lab? All right, so let me tell you who's gonna come in next week. So you're gonna take a note so that you know exactly when you are coming. So I said last time that I need to, because this is a full class and we only have so many stations in the lab room. You cannot all come, you know, show up to the lab room at the same time, which is unfortunate, right? Even in the spring, I don't know what we're going to do in the spring, but in the spring semester, but it's because these lab rooms require different equipment than, for example, the labs 1 and 2, where you can actually all go there at the same time. But we're doing the best we can given the limitations. So I'm just gonna read out 7 names, and these 7 students will come in next week at let me do this carefully. Otherwise, some of you are gonna show up there at the wrong time, and then we're gonna be so we are here. This is our 4th meeting together. So next time, September 30th, some of you will meet me in the lab, and the other ones will just stay home and work on the simulation so that you are ready for when you actually come in the lab the week after. So I'm gonna read 7 names now, and these 7 names that I read out will come or will join me in the lab next week. So I have Ryan, you there? Ryan? Adil?
Yes.
You there?
Yes.
Christina?
Here, Professor.
Julianne? Pooja?
Here, Professor.
Sichuan?
Here.
Mustafa?
Here, Professor.
All right. So I need to hear Adil. Are you here? What happened? You
Yes,
don't have a
I'm here.
microphone? Ryan?
Yes, Professor.
All right. So all of you 7 will join me next week in the lab. So the room is 649. So you should have your VAX pass, or you know, whatever they ask you to show when you go into the lab room, right? You will join me there at 9:30 a.m. and we're gonna actually work on the motor itself. And a lot of things will happen when we are in the lab room. We'll explain things, and it'll be your first time working with the assignment. So the rest of you, Michael, Jeremy, Edgar, Tyler, Haresh, and Jeffrey, you will join me in the lab in October 7th. So we will alternate the classes. So whoever comes in the next week, then we come out, you know, 2 weeks after that. So the week we don't meet, you will actually receive the assignment that you're supposed to work on so that you can do the simulations before coming into the lab. So it'll be the same thing we're doing. You will receive assignments like this. You will read them. You will try to reproduce the specific responses that you are being asked to produce. And then when you come into the lab, you will actually verify these responses. You will collect, you know, actual measurements from the device, and you will be able to compare these 2 responses so that you can convince yourself that what you are doing in the simulation is very, very, close to the actual behavior that you will see when you work with the physical system. So now let me just say something about how this thing actually works in the lab. You will be set in a computer. You will have access to a computer that has this software. So from this software, you can control the actual machine, the actual mechanical board and the mechanical machine, and the actual control board. So all of this will be done through software. So that is why we cannot just install this in our computer, because this is copyrighted software. And this is they only grant out license for specific physical systems that we have in the lab. So we only have 7 of them, 7 of these things. So that is why you can only I can only have 7 students at the same time. But anyway, all the details about how this thing works, I will give at the very beginning next week at 9:30 a.m. So for the rest of you, there will be no Zoom meeting. All you have to do is finish assignment number 3, submit it by next week, and then be on the lookout for the next assignment. Then you can work on the simulations that this assignment is asking you to do. If you have any questions, you can email me so that I can help you out. But once you do that, when you come into the lab on the 7th, you should be able to reproduce whatever your simulations gave you. Now, for the other students that come in on the 30th, you will do the practical aspects first. You will capture, or you will take the measurements from the machine, you will capture the responses, and then the week after that, you will go home, you will work on the simulations, and then you will compare them. This is so that all of you get to do the same exact, you get to cover exactly the same material, but you will do it in a different order. And that is the way it's going to work out. All right, so are we all clear on what's going to happen for the first 2 weeks? We're going to see how you guys adapt to this. I want to be, I want to make sure that you get the full picture as to what it takes to use something like this. All right, so we're going to see how this works out. I may have to adjust our calendar, to meet our progress when we are in the lab. So you should expect an email from me containing a different syllabus or an updated syllabus, or assignment calendar soon in the next 2 weeks. But for now, this stays up to the 5th session. This will stay exactly the same. All right. Any questions? Is anybody going to school at all this fall semester?
I am.
Yeah,
Okay.
I am.
All right, so there should be no problem for most of you, right? If you have issues, or if you have impediments to going into these meetings in the lab, you should let me know privately via email, and then we can try to resolve these things. But if not, I think that's all I wanted to say. Are there any questions before we end today's session?
So for the week that we don't go to the lab,
Yeah.
The lab report is still due, but we just don't meet online. And then the week after that, we meet in the lab.
Correct. So you will submit all your reports via email whenever they are due. So that's why I said, right, I will eventually need to update this email to change the due dates, right? So yeah, if the due date falls on a week where you do not come into the lab, you have to email it to me. Or if it falls in a date where you come into the lab, you will still have to email it to me. So whatever happens, all the reports will be submitted via email. All right, you do not have to print anything, but these due dates will eventually change according to how we adapt to the lab, right? I want to have at least 2 sessions with all of you so that we can know what's going on and whether we need to actually review some of the material for the first 2 labs using the actual equipment. So there will be some changes to this calendar, but I will make sure to keep you all updated as to what they are. So Tyler, for now, right, we just have an assignment due next week, and then we're going to start changing things up, and we'll take it from there. Okay.
Okay, thank you.
Anybody else?
Yes, quick question, Professor.
Yes.
For those that are us that are going physically to the lab, will you be sending over like what are the I guess we will be doing during our lab time, or is that discussed once you get to the actual room?
I mean, for every assignment that we have left, you will receive an assignment like this,
Okay.
just like we've been doing, right? So now, in addition to this, you will get a chance to go into the lab and actually work on this assignment using the machine so that you can compare them, right? So you can think of the, the class as staying the same in terms of the assignments. You will receive all the assignments that we will work on from me via email. You will receive them, except now the dynamic will be slightly different in the sense that you will do your simulations at home on the week that you do not show up to the lab. But when you do show up to the lab, you will actually take, practical measurements and then compare them in the report. Does that
Got
make
it.
sense?
Yes, that makes sense. Thank you.
All right, so that will be the only change to this. I mean, I want all of you to get some exposure into the lab so that you can see how all of the things that you've been doing actually make sense, right? And they are physical things that you can actually see with a machine. So yes, you will receive an assignment that looks like this for every time you actually I want to introduce a new topic. There will be 7 of these, 7 assignments. I was trying to figure this out, how this is going to play out. We're going to actually do 7 or 8 assignments as opposed to 9 that we have in the calendar. So there will be 7 or 8 assignments depending on how we adapt, but they will all look like this, right? You will be expected to do simulations using the MATLAB code that we've been using. And when you go into the lab, you will reproduce these things in with the machine. You will see how they differ. Of course, they will not be exactly the same, right? Because one of them is theoretical and the other one is just the physical thing. So these plots may not look as smooth as you see them here, but it will the concepts will still apply. The general concepts as to what a PID controller will do for you or can do for you will still apply. You will be able to see them either way, either in the lab or in the through simulations. So let's try not to be confused here. If you have any questions as to what's going to happen, please email me. Do not just stay there confused. There should be no confusions here. I want to be as clear as possible. So some of you will meet with me next time, and the rest of you will meet with me in 2 weeks' time. But every time you do not go into the lab, you will have something to do. And if you're not sure what that is, you should email me. In other words, when you don't go to the lab, you just have to do some simulations according to the assignment. And then when you do go into the lab, then you'll do the other part. So the punchline is every assignment will have a theoretical part and a practical part. You will take care of a practical part in the lab, and you will take care of the theoretical part at home using the MATLAB code. All right, so any other questions?
Both the practical and theoretical will go in the reports.
Yes, so that is why this will be updated. Maybe depending on how it goes, you may need to 2 weeks for each report as opposed to only a single week, right? But because I want to see how we all adapt to this, then we'll figure this out. But yeah, so because you're gonna go there every other week, I may have to adjust the due dates for the report. So you may eventually get 2 weeks for every lab as opposed to just 1, because there's more things to do for every assignment, right? Up to now, we have only been doing, simulations using the theoretical parts, and then you submit a report almost every week. But eventually, because we're gonna do more for a specific assignment, then I should adjust the report, the due dates accordingly. So everything will be fair. I hope it'll be fair. I will try to give you enough time to complete this, right? Because my job is not to just give you a hard time. My job is for you to be able to see that this is something that is useful, and so that you can get something out of this. All right. So I want to be fair as possible, and I will keep you updated on what the changes to this calendar will be as we go through as we meet in the lab. All right. Any other questions? You'll enjoy the lab. This machine is pretty cool. It's a cool thing to play with. And if there are no more questions, I will see you, some of you next week, and the rest of you 2 weeks from now.
Thank you, Professor.
All right, bye-bye.
Thank you.